Okay, so we're going to pick up where we left off, and so this is volumes of cylindrical shells, part 2. So where we left off is we were looking at, we had a solid here. Okay, so we had a solid here, looked something like this. So we were doing this graph here, and the x-axis. So I rotated this around and got something that when cut in half looks like this. And we went through and we came up with a formula for the volume. The volume was the integral 2 pi x f of x dx. And something I want to point out is, it works for solids that look like this. I have a graph that's bounded by the x-axis, and it's rotated around the y-axis. So this works for those kinds of things, but in general, what you're looking for is you want to write down, this 2 pi x. You can think about that as the circumference of the circle created by the cylindrical shell. So this distance, here, let me erase some of these lines. So this distance down here is x. So the circumference of that circle is 2 pi x, and then you multiply that by the height of the shell, and that gives you the area of the cylinder, and then when you integrate over dx, that gives you the volume. So then in general, we want to be able to draw these things, write down, the circumference of the circle and figure out what the height is. We're going to see some examples where it's not just, the function there. We're going to have to be a little more clever. So just a heads up there. Okay, so let's jump into an example. So example 1. So this is so we're going to do the problem that I've drawn up here. We want to find the volume obtained by rotating the region enclosed by the graph y is equal to 2x squared minus x cubed, and y is equal to 0. About the y-axis. So we're going to take this graph and we're going to take this this region and rotate about the y-axis like I've drawn up here. Just one other note, so I haven't been writing it in here. It's kind of been implicit. This needs to be a definite integral. I don't want to get a function out of this. I want to get a number. I want to get a volume specifically. So add integration bounds in there, a to b. So I'll draw it one more time. I'll label stuff. So I have, this function that looks like this, and the x-axis down here. I'm looking for, I want to find the volume obtained by rotating that region around. Let me just point out that this one here is the graph y is equal to x squared, 2x squared minus x cubed. Okay, so I can write down my formula because I used this picture to derive it. So volume is the integral 2 pi x f of x dx. And now, so I have the integral from a to b. Let's go through and figure out what our integration bounds are first. You can do, you can set up the integral for it first if you want. But we're going to need to find these integration bounds eventually. So if you look back at this picture, so you can obviously tell, so I'm going to be integrating along the x-axis down here. We obviously start at x equals 0. And then we have to figure out, okay, where do I end up? And where I end up is this point here. So this is the x-intercept of the graph of 2x squared minus x cubed. So to figure out the b value for our integral bounds, we're going to find the x-intercept of that function. And so just kind of a note, we're always going to be integrating, along just half of this thing because, so I start at 0 and go here. I don't start, on the left here. I don't start on the opposite side. That would give me twice what I want. Here I'm just trying to find all this part over here is taken into account by the factors here, so I don't need to include those. I'm always going to integrate only over, half the picture, really. Don't get too hung up on that. I just wanted to point out why I wasn't integrating, from one side to the other. Okay, so our integration bound. So we want to find the y-intercept, the x-intercept of y is equal to 2x squared minus x cubed. And of course, to find the x-intercept, we set y equal to 0. We get 0 is equal to 2x squared minus x cubed. And so we can go through and solve this, factor out an x squared. And this tells me either x is equal to 0, which we already saw, or x is equal to 2. And that 2 is going to be my integration bound. So my volume then is going to be the integral from 0 to 2 pi x f of x dx. And now I'm just going to plug in. So you can see in the picture, my height here is just given by, the graph of 2x squared minus x cubed. So whatever that height is the height of my cylindrical shell. So this is then the integral from 0 to 1, 2 pi x, and f of x is 2x squared minus x cubed dx. And now we can just do this integral and it gives us our volume. I'm going to take the 2 pi out of the integral because it's a constant. I'm going to distribute the x into the parentheses there. I get 2x cubed minus x to the 4th dx. So this is 2 pi times the integral from 0 to, we can do this integral now. So now we're going to do this integral. So just do the reverse power rule, get 2 over 4 x to the 4th minus 1/5 x to the 5th when I do that integral, evaluated from 0 to 1. And when we plug in, we're going to get 2 pi times 2, we're going from 0 to 2. Yeah, so I just copied that. 0 to 2, 0 to 2. So I wrote it right in the first one and then for some reason copied a 1. So we're going from 0 to 2. So I get 2/4 times 2 to the 4th. 2 to the 4th is 16, minus 1/5 times 2 to the 5th. 2 to the 5th is 32. So this is 2 pi, 2 over 4 is a half, and you have that 16 there. So this is 8 minus 32 over 5. And when you do the simplification, so you multiply and divide 8 by 5, get a common denominator, you're going to get 16/5 pi. So let me draw that a little more legibly. 16/5 pi. And that's the volume of that region. So, so this formula we derived here works for, things that look like this. I'm about to do an example where we can't just, write down this formula. Really, you want to think about it as, you want to find the circumference of the circle, the circumference of the cylindrical shells, and multiply it by the height of the cylindrical shells. Let's see an example where we actually have to think about it. So this is example 2. This will be the last example for this video, trying to keep them a little shorter. So we want to find the volume obtained by rotating the region enclosed by y is equal to x and y is equal to x squared about the y-axis. So first thing you're going to want to do is always draw a picture, just so you can tell what's going on. So we have the graph y equals x. y equals x squared. And you'll remember, if this is looking familiar, we did this problem. Let me draw a little bigger because we're gonna have to draw on it. We did this problem before with washers. So this was something from the washer method that we've already done. So now we're going to do it using cylindrical shells. So I need to see what my cylindrical shells are. And in this case, these shells don't go all the way down to the x-axis. So you'll notice that the shells that I'm interested in only lie, inside here. I didn't do a good job of drawing a symmetric. It's supposed to be. Let me fill in the solid here so we can see what's going on. So connect those. Those get connected, I guess. Well, yeah. So this is, half of the cylindrical shell. So now we're going to set up my volume. It's the integral of the circumference of the shell times circumference times the height. And, and also you have to, so in order to figure out if it's dx or dy, you have to look at the length that you're multiplying through. So because I'm multiplying, because I'm extending the cylindrical shell in the x direction, so it's a circle that's been extended along the x-axis. This is going to be dx. So in order to see that, if you're looking down at this cylindrical shell, the direction that I extend the shell in is in the x direction. So this is dx here. So that gives us our integration variable. So it's a little different than the ones we had before. It actually ends up being the same, but you have to think about this a little harder. You have to think about what direction am I extending the shell in, and in this case, I start with this circle and I extend it out to this circle, again looking from above, and that's just that extension happens in the x-axis in the x direction. So that's why I have a dx here. So let's go ahead and plug in, and then also not forget our bounds here. So let's write down expressions for the circumference and the height. So the circumference then, if I look at one of these circles, it's going to be 2 pi and then times the radius of that circle. Well, that distance down here is just x. So it's whatever my x variable, whatever my the distance along the x-axis I'm at. The height is a little different. So the height that I'm talking about here is this one. So it's just that height there. And the way I get that is, I take so I want to find, this. So let me erase some of this so you can see what I'm saying. I want to find this height here. And that's just going to be, x minus x squared. So I take the top function minus the bottom function, and that'll give me the height. Go back to black. And again, it's not just one of these functions because I'm not integrating down, or I'm not letting these shells fall down to the x-axis. I'm integrating between two curves. So because I'm going between two curves, I'm gonna have to subtract those at some point. And now let's find our bounds of integration. So I'm gonna probably need a new page. Yeah, so let's do a new page. I don't have to write super small. So bounds of integration. I'll go back to the previous page. Stop talking while I'm writing. So in order to figure out our bounds of integration, first thing we should notice is, okay, I start at x equals 0. And I'm going to go down to this point here. So I need to figure out, because I want to figure out the x value there, I need to figure out where these two graphs meet, where they intersect. And so to do that, I'm going to set the two functions equal to each other. I'm interested, so the bounds are given by where x and x squared intersect. That happens when x is equal to x squared. So if I go through and solve this the way we're supposed to, you get x squared minus x is equal to 0. So this implies that x times x minus 1 is equal to 0. So I get x equals 0, x equals 1. And now I can plug this all into my integral. So my volume then is the integral from 0 to 1. So let's look back. It's going to be circumference times height. My circumference is 2 pi x. The height, looking back, I've written down as x minus x squared. And the thickness of my shells is dx, one way of thinking about it. And now we just do this integral. Factor out the 2 pi again, 0 to 1. And then distribute this x squared minus x cubed dx. Okay, so this then is 2 pi times x squared over 3 minus x to the 4th over 4, evaluated from 0 to 1. And when I plug this in, I'm going to get, when I plug in 1, I get 1/3 minus 1/4. And when I plug in 0, I get 0. And now this is 2 pi. So we have 4/12 minus 3/12. This is 2 pi over 12. This is pi over 6. And that's going to be my final answer. So again, the thing you need to be careful, and the thing that makes these problems the thing that makes these problems hard is that, you have to be able to work with these, you have to be able to draw these things and then figure out, okay, what is my circumference? What is my height? But once you do all that, it's actually not too bad. It actually comes together pretty easily. So I'm going to stop there. Start a new video, do some more examples. So